See it on there.
Oh, is that happy on there? Oh, darn.
Yeah. I got some notes in the presenter mode, but I'm not really sure how to do that, so I'll just hopefully remember some of it. No, ask Ronnie. All right. So that first one's a bit more technical. This won't be as theoretical, so should be able to relax a little bit. So I'm just assuming that most people are doing this unit, or that everyone's doing this unit, and most people haven't done the radiotherapy unit and haven't covered linacs and all that kind of stuff. It's not too important, but if you have done the radiotherapy unit, some of this will be a little bit basic. Okay, so some aims. So in my presentation, I just wanted to make a connection between the theory that Barney's talked about and what we do in clinical practice. Give a very brief introduction to linacs if people haven't seen them or know how they operate or how they work. Talk about international metrology, what it is, why we need it, primary standards, the IPM and ARPANSA, calibration of our reference ionization chambers that are traceable to that primary standard at ARPANSA, and yep, as I said, measuring dose in the clinic and applying all those correction factors that Barney was talking about. And as Barney's already mentioned, the scope is just MV photons delivered using C-arm linacs. So just keep in mind, you can have all different types of radiation, protons, electrons, heavy ions. You can have different machines, which will have different protocols, CyberKnife. This is just MV photons on C-arm linacs. So that's what a linac kind of looks like. That's a Varian true beam linac, if you haven't seen one. And that's Elector, so they look slightly different, but they have the same basic concepts. They're the workhorse in radiotherapy. They're capable of producing X-rays in the MV range and electrons as well. And this is through accelerating electrons up to almost light speed, smashing them into a metallic target like tungsten, and producing X-rays through Bremsstrahlung interactions. So that's the kind of inside of a linac or diagram, but all we need to know for now is this one. So I think next unit you'll know all those parts, or most of them. So essentially you have a power generator that feeds into an electron gun, as well as the waveguide itself, and sets up resonance of a microwave, which accelerates those electrons. They're then bent downwards to the patient and hit a target to produce the photons. They're also collimated, so you end up getting this kind of conical shaped beam coming out, and then collimated again, so that beam is defined as a square or a rectangle. So when we talk about field size, we're talking about in one plane of that beam, what it would look like as a cross section. So they're rectangular or square size. Yeah, so as I said before, trying to get that connection between these kind of pictures that you would have seen in your notes and in lectures, and then in practice. So how is absorbed dose actually measured? How do we know what a gray is? What is absorbed dose? We know a gray is joule per kilogram, but we don't know how much mass is actually in an ion chamber. So how are we going to get joules per kilogram if we don't know the mass? Also, if we did know the mass, they're vented to the atmosphere anyways. So we have to have some kind of way of linking what a gray is. So that brings us to primary standards. So everyone's familiar with primary standards for things like mass. They used to have real life artifacts like the meter, as well as the mass. And now everything's moved to definitions in terms of fundamental quantities. So for MV beams, this is the primary standard. It's a graphite calorimeter. So this is held at a place called ARPANSA in Melbourne. Oh, I've given it away. That was meant to be the next question. I was going to ask who maintains them. Is it hospitals? No, it's not hospitals. End users, like physicists, no. It's Pedgman. It's not Pedgman. ARPANSA, so I gave that one away. So that's in Yulumbi. Yeah, if you say Pedgman, you might get a mark. It won't be right though. So that's the front entrance. I was there last month for a few days on a course, and got to see some of the the primary standards themselves and some of the machines. Yes, yeah. So to kind of understand what our panzer is and how they fit into the big picture, we have to go back in history. So a bit of a few boring slides, but in 1875, the Meter Convention was signed by representatives of 17 nations. So this established a permanent structure for member governments to act in some kind of common accord relating to all kind of units of measurements. They created the BIPM, which people have probably heard of. A few other things as well. One of them, more relevant ones, is CIPM. So now has 55 member states, and Australia was one of them in 1947. This is the BIPM, also really nice front yard. It promotes the global comparability of measurements. It's an international primary standards lab in Paris, so everyone compares to this lab. And this is for all kinds of standards, not just dose, obviously. Under the BIPM are RMOs, or regional metrology organizations. So we're part of APMP in our region. You have regions in Europe, Africa, and so on. And as I said, they compare values of standards amongst each other, and they also advise that CIPM on a mutual recognition arrangement. So basically saying that they agree their grey is equivalent, their methods are equivalent, their uncertainty is equivalent between all different regions and centres. And so the way our panzer fits into all of this, finally, is we have a National Measurement Institute in Sydney, and they authorise our panzer to maintain the dosimetric standards. So our dosimetric standards are actually maintained by our panzer and not our primary lab, I guess, for Australia in Sydney. They authorise our panzer to do it. So the question is, why bother with all this? International metrology is important. So if you have a clinical prescription of absorbed dose, this will have been based on any research or studies that has international involvement. So if you have results that came from America or somewhere else in the world, you want to make sure that their grey is the same as our grey, and everything's just consistent. Also want to note that there's also secondary standard labs that fit into this picture that have their standards calibrated from the primary standards labs, just so you can have all users have their instruments calibrated. So there's probably not enough standards labs to do it all by themselves. Going back to primary standards, now we kind of know what our panzer is, how they fit into the big picture. That's a cross-section on the right of a graphite calorimeter, which you can see on the left there. That's the primary standard for MV beams maintained at our panzer. You can look at a simpler kind of schematic. Essentially, it has a few main components. At the very middle, a small, not the very middle, but a small core containing temperature sensors, measuring temperature, as well as heating resistors. And this all operates within a vacuum to minimize heat losses. So you have a core, which is within a graphite jacket and a vacuum seal, a second graphite jacket, and then the whole phantom is graphite. So why graphite? It has radiation interaction characteristics somewhat similar to water. It's quite easy to machine, so you can create the calorimeter with relative ease. Using those vacuums, there's very little heat loss compared to something like water. It's a bit harder. It has a lower specific heat capacity than water, so you can heat it up quicker with the same amount of dose, so it's a bit more sensitive, and it's easy to maintain. So how do they work? So when I wrote this presentation, I looked at your table of contents and timeline, and I thought you hadn't covered these yet, but if you have covered these, apologies, it's a bit basic. So they work, there's a few different ways they can operate. I'll just mention how our panzer operates them, but the essential principle is that dose is related to a change in temperature induced by radiation, and that change in temperature is equated to electrical heating of that calorimeter. First of all, you'll heat it using an electrical heater with a known power to get a temperature over a time. This is in the wrong order. You'll also then irradiate it and measure that temperature rise in the graphite core. So the way you measure the temperature rise is through those thermistors, and they actually change resistance as they change temperature. So what you're technically measuring is a voltage change. you can infer a temperature change from that. And then you just equate the electrical power that it took to create a certain temperature change to the radiation power for that same temperature change. As I said, there's a few modes of operation. Our Panzer uses this quasi-adiabatic mode where you do two separate runs, so that electrical calibration and then the irradiation. There's other modes where you can do half-half. You heat it up and then you start irradiating, and then you heat it up and you irradiate it, and you try to match that same gradient or temperature increase. This is the way our Panzer does it, and you get this kind of graph, so you can see that change in voltage over time. And so you can, from your change in voltage, if you multiply by a few correction factors and conversion factors, you can end up with the dose to graphite in joules per kilogram. Of course, we want dose to water. So to convert to dose to water from dose to graphite, they use Monte Carlo modeling. They model the calorimeter on the computer and do a simulation between water and that calorimeter itself and get a ratio at the same location. And then by timesing your measurement from your calorimeter itself by that ratio, you can get dose to water. So finally, after we have absorbed dose to water defined at a point, and it's been calculated using this primary standard of high metrological quality, we can place an ionization chamber at the same point, take a measurement of that same amount of total energy that you just gave the calorimeter. So that could be measured in by time, for example, if you had a cobalt 60 unit. I'm not too sure if you guys have learned about cobalt 60 units and linacs. But cobalt 60 unit basically just has a real actual radioactive source in it that's constantly emitting radiation, so you would measure it in time. Anyway, so you can get the calibration coefficient by placing your chamber there, measuring that response. You know your dose, you've got your charge from however much is read off the electrometer, and this is your calibration here from the primary standard. So that known absorbed dose divided by the reading of the chamber, and this is in grays per coulomb. Usually on the certificate, they'll give it in, I think, milligrays per nanocoulomb, all the same stuff. Just a side note, they also have a water calorimeter now. They're just currently commissioning it, so they're going to swap over to water calorimeter. The obvious benefit is that you don't have to do that conversion between dose to graphite and dose to water, so you can actually lower your uncertainties. But there are a lot of other correction factors and things you have to take into account when using the water calorimeter. Calibration traceability. So it's not feasible to perform the absolute dosimetry directly to all user linacs. So we can't get that graphite calorimeter, bring it over to Sir Charles Gardner, model our linac on a Monte Carlo sim, do all that kind of stuff. So what we do is we have a calibration chain that's traceable from primary standards lab. And I think you guys have learned about that in the current unit. And the kind of terminology we use is reference chamber is the one we send to our Panzer, which is in Melbourne, for calibration against that primary standard, so the graphite calorimeter. And that reference chamber is now said to have the secondary standard, so we transfer that across from the primary one. Once that's returned back to us at the hospital, we use it to calibrate all of our other ionization chambers. So we don't use the reference chamber for routine measurements. It maintains that direct link to the primary standards lab, and we don't want to break it, lose our connection to the primary standard. Also, we want to have a lot of different ion chambers that we can take measurements with. So we do what's called a cross calibration and transfer the standard again to a field chamber. So it'd be a good idea to remember those terminologies: reference chamber, field chamber, primary, secondary standard, tertiary, that kind of thing. Oop. Yep, so I've just kind of put up the flow, primary standard to secondary to field. And then maybe if it's a secondary standard lab that you have your ion chamber calibrated at, the primary would have transferred down to the secondary and so on. It's just a chain all the way back to the primary lab. But at our hospital, we send ours straight to our Panzer, and they have the primary standards. This is the process. Okay, so when you get your chamber back, you'll also get a certificate. This is really important to kind of C, it has your calibration coefficient. Like I mentioned before, you can see this one's in milligray per nanocoulomb. It's important to note that this coefficient is valid for very specific reference conditions. They've listed their reference conditions of how they took the measurement here. The polarizing voltage, the reference point that they took the measurement at, the geometry of the setup, field size, the depth, the energy, the temperature, the pressure, all these kind of things are important. And that coefficient only applies to those conditions. Any departure from those conditions you have to correct for. When we perform dosimetry under these reference conditions, we call it reference dosimetry. So it's another just terminology thing. And in Australia, we use IAEA's TRS 398 as our code of practice for reference dosimetry in MV beams. We also use this for electrons as a side note. So this code of practice, it's a good idea to look through it, especially that chapter 6, I think it is, for MV photons, as well as some of the initial chapters which give information on, information framework, that formalism of NDW and practical implementation. It talks about a lot of those things that Bryony talked about, the different types of ionization chambers, why I would use one over the other, the recommendations of when to use one over the other. So this is a really important document. I think a lot of exam questions will be related to that as well. It supersedes a previous report, TRS 277. So we used to have a primary standard based on air coma, not absorbed dose to water. And so there had to be a conversion between air coma to absorbed dose to water in clinic. And it was a lot more laborious to actually perform reference dosimetry. There's more uncertainties, it's less robust. So now we have this absorbed dose to water standard from a while ago. I mean, 1998, I think is when this first TRS 398 came out, and they're updating this. It should probably come out in the next few months with a bit of an update, and a few things will be clarified in it. Did I miss anything? No, it's got other beams, electron beams, proton beams, heavy ion, but we're just focusing on photons now. So reference conditions, how do we set up two reference conditions? So this is in TRS 398, it's just table 6.2. This is all the conditions you have to use when performing reference dosimetry, so you can apply that factor. The phantom material should be water, shouldn't use a solid water if you're doing proper reference dosimetry. And so we just fill up an actual tank of water and put it on a platform. This is meant to be like my linac head and beam. The chamber type should be cylindrical from Bryony's presentation. The measurement depth, so this is, I think you guys have covered TPR 2010s, and I'll kind of give a brief idea of what it is. Just think of it as a metric for beam energy or quality, or the energy spectrum of a photon beam. But generally we measure it 10 centimeters deep in water. Reference point of the chamber and positioning of it, it's the geometrical center of it, and we place that right at 10 centimeters deep. And then finally, the last few are just talking about your field size, as I mentioned before, in that cross-section plane where you're measuring at should be 10 by 10 centimeters, and the distance from your source to your dosimeter itself should be 100 centimeters. So we're placing that at isocenter. Isocenter means much to you guys. So after we've got this set up, we have our chamber connected to electrometer, we have voltage applied, we're ready to perform reference dosimetry. We irradiate the chamber and we're going to get some kind of charge reading from our electrometer, which is MQ in this equation. So this equation is really important to know. NdWQ naught is our calibration coefficient. Note that's the Q naught subscript says that they did that calibration in a cobalt 60 beam. That's what Q naught means. So this is really important. We don't have a cobalt 60 beam. Cobalt 60 beam, we've got the exact energy, 1.25, the average, something like that, MeV, MV. But our beams are 6 MV, 10 MV. So we're going to have to make some kind of conversion. So apart from those correction coefficients that Bryony mentioned, which is I've written as the product of Ki there, we have KQ Q0, which is a correction for beam quality. So that's a very important one. And the way we do this is on that same certificate I showed you before that has our calibration coefficient, we're given this graph. So our pans also have a linac themselves with 3 energies, 6, 10, and 18. And they use our chamber to measure KQ for those different TPR 2010s and plot it on this graph. They then fit a polynomial to it and give you the fit in the certificate. So you can see here the equation and the parameters or constants for the fit. What we will then do is use our chamber and in our beam with our own qualities. And yeah, we have 6 MV and 10 MV, but it's not the exact same in terms of the whole entire spectrum. That's your nominal energy, but no 2 beams are the same. So we will then take a measurement of TPR 2010 in our beam with that chamber, plug it into here, and get our own KQ or our own correction for beam quality. So this is an important one to understand. I think this one can be confusing. If you don't get that one, definitely ask a question. So TPR 2010, I think you guys actually have covered this by this point. Essentially, it's just a ratio of doses at 2 different depths using the same distance to the chamber. And it's a good metric, as I said before, for characterizing the energy spectrum of a beam. You can't measure the actual energy spectrum of a beam, but this is a good metric for that. So this is more on the practical or the clinical side of how we do it. This is our log of our spreadsheet at Charlie's. So as I said, after we take our TPR 2010 measurement, we can plug it into here to get KQ values. So these were directly from the certificate, TPR 2010s, the KQs, the fit parameters. And so once we've measured ours, we can get our own KQs. So that's KQ covered. Calibration coefficient from primary to secondary, just here. So that's directly from the certificate. You can see 48.31, and this one's in gray per nanocoulomb. And for each energy, we'll measure the recombination and polarity corrections, and then cross-calibration. So this was our reference chamber, and as I said before, we need to transfer that to all of our field chambers. These are the chambers here on the left. You can see for 6 MV, 10, 6 FFF, we have our cross-calibration factor, as well as our corrections for recombination, polarity. Okay. Too sure what's going on there. It's in an infinite loop of putting boxes up. Okay, so from that kind of log, or where we store all our data for each chamber, we have this kind of spreadsheet for our actual measurements or output measurements once we have our setup. So we'll put in the type of chamber we're using, and then from that table before, it's going to pull all the relevant data. We put in our temperature, we put in our pressure, and you can see these factors here came directly from that previous table. So KS was our recombination factor that we calculated with the chamber. Our Cal factor, this is a cross-calibration factor from the reference chamber. So again, I just want to stress this is a field chamber at this point. Kind of has like a tertiary standard. Polarity, temperature and pressure correction, and then everything combined. Now this PCF one I wanted to mention, this is because in monthly measurements we don't use water. If you're doing reference dosimetry, strictly you should use water for determining the true dose at that point. If you're doing it just for your QA, you can use solid water. TRS 398 says that's okay. You just need to have some kind of factor that converts between the two. So that's PCF. So once we have all our factors from the certificate, all our measurements, we take a reading in nanocoulombs from our electrometer, times by all of those coefficients and correction factors, and we end up getting our dose. And that's, I want to stress, that's a dose for that point, for these conditions. You change anything else and it will change. You change your field size, your SSD, all of those things will change the dose. So we relate everything to that one point and one set of conditions through a set of other factors. So yeah, that's everything I have. Thanks for listening. Yeah. If you guys have any questions or if like something wasn't quite clear on a slide, I'm happy to discuss it. Questions from Brian? It's a good question. I got asked that and I got it wrong, but I think it's like, I'm not sure exactly what they recommend, but I know we do every like 2 years, essentially, yeah. Or if you damaged it somehow, you want to make sure you have that standard still. But yeah, I think we do ours every 2 to 3 years. And the must have. Yeah, it's just in the cupboard. But there probably is a recommendation. I probably should know. I think 2 to 3 years. Any other questions?
I know when you went to ARPANS, did you get to like check out any of like the medical physics more stuff?
The what?
Like the actual or like the graphite one?
Yeah. So I got some pictures with that one itself like that.
Oh, so those are your photos, yeah.
That one I got from the internet, but yeah, I got pictures like nerding out next to it like that, and some other ones. I saw the water calorimeter. We did a few practicals. Saw their linac. Yeah.
Yeah, I was about to say that looks way too nice to be put.
Wow. Any other questions? Does everyone understand the KQ factor? Because it really confused me when I was doing it. Maybe it was just me.
You could go through that.
Yeah, so do you understand the concept of 2 6 MV beams not being exactly the same from 2 linacs? Does that make sense or not really?
Related to the quality line difference across the energy spectrum.
Yeah, so they won't have the exact same spectrum. So a 6 MV photon beam, you're using 6 MeV potential or 6 MeV electrons to create it. You're only going to have a few photons actually at 6 MeV. The rest are going to be some kind of continuous shape from 0 to 6. And that shape won't be exactly the same for 2 6 MeV beams from one linac to another. And you can characterize that spectrum essentially using TPR 2010. It's a good metric for it's kind of also penetrating power of the radiation, which is related to that spectrum. And so your chamber is going to respond differently, even if you're giving the same amount of joules total, same amount of energy, but with photons of a different energy, your chamber will respond differently because it has some energy dependence. So because we get a calibration coefficient from our Panzer from a cobalt-60 beam of energy 1.25 MV, something like that, we need to then convert it or convert our readings from our chamber itself to something that came from, let's say, a 6 or 10 MV beam. So every single beam and quality we have is going to have a different KQ. So I think, did I have this spreadsheet? Okay, so I have the KQs here because it gets a bit more confusing. But when we do our cross calibration, the KQ kind of gets absorbed into a factor, into that calibration factor itself. But you can see the ones that our Panzer gave us for their linac in their beam. So even though they made that nice graph of KQ versus TPR 2010 with their linac, we then need to find our KQ value for our TPR 2010. So we know that it's chamber specific. So that's just one of the ways you can get KQ. A lot of standards labs didn't used to have a linac, and so you'd have to use generic values from literature for that specific chamber, and it doesn't take into account chamber to chamber variations, or you could calculate it theoretically using Bragg-Gray. So yeah, that's a bit about KQ. But if you read TERRA 398, it's got every little way you can find KQ and all the information about it. Yep.
So each KQ value is attached to each individual linac, yeah?
Yes, kind of. So I'm pretty sure but our center, our linacs are very much beam matched. So we can use the same KQs for all our linacs. When I pull up my spreadsheet for a measurement, I'm fairly certain the linac itself doesn't change the KQ. It's still got the same one for the chamber. Just because of how beam matched our linacs are.
Yeah.
But the one at our Panzer isn't the same.
Because I was going to say, like, if the patient had to receive multiple treatments and went to separate linacs, you'd have to correct between those. But
yeah.
They're being matched.
Yeah, they're being matched. Yeah, and we define the output every month for every linac anyways. But yeah. Any other questions? No. Cool.
Thanks so much, Andrew. Thanks for running. Thanks everyone.
Thanks for coming. I had too many colored boxes.
What are you trying to talk about now?
I was trying to highlight certain things and then